My name is Edil Medeiros, and this is the first time I'm doing this workshop, and I have to confess that I'm not a specialist in Cash, but quite the contrary, actually. I proposed to do this workshop here to force myself to learn at least the basics of Cashu. I was curious about this kind of technology for quite some time. What I'm trying to do here today is talk real quick about the eCache basic theory, how it does work, at least on the Cashu side. Then we are going to talk about Cashu specifically, which is, it's okay because, okay, yeah. Let's talk a little bit more about Cashu. And Cashu is a web-based protocol, so we are going to have some HTTP endpoints to look at. And then I wrote here coding together, but given the time, I will be pretty much coding myself and showing whatever I'm doing. I think it will work better for the time. So what I'm going to show you is how it does work to acquire some eCache tokens, what we have to do to get some money on this system, and the other way around. How do I redeem my money back on these Cashu banks that they call mints? If you want to follow along, there is a GitHub repo. You can use this QR code if it makes it easier. It is supposed to have a lot of different branches, and there's a start here branch. There's the master branch, where is the solution for a Cashu wallet that I wrote for this workshop. Please don't use this in production. It's totally unsafe thing to do, but it's made to be easy to understand, not to be secure. And it's, of course, not complete. Of course, PRs are welcome. Sure. Eu não te escuto. Sorry? It's not public. It's not public. Just a second. Settings. Oh, my bad. Change visibility, public. I want to make this change. I have read whatever. Make this public. Might need this. Oops. Maybe I need some help. My bad. Maybe it's public now. Can you check it, Leo? Yeah, sorry, my bad. There is a start here branch that has some starter code, and there are other branches, and the README is supposed to guide you on whatever you should do if you're doing this by yourself. I think everyone is okay with that. Just real quick here, who I am. My name is Edil Medeiros. I'm a professor at the University of Brasília. It's the capital of Brazil. It's a very nice, modern city, a little bit communist architecture, maybe. There are some folks that like it. It does worth taking a weekend and visiting. I'm also head of research at 21. 21 is a nonprofit in Brazil that funds open source developers. We have some grantees here. Pins was presenting a workshop earlier today. And we also work on Bitcoin education. We have this program called the Bitcoin Dev Launchpad that we are going to have a new cohort running in 2 weeks. We have a lot of folks around that were in the first BDL cohort, so say hi to them. I'm also a co-host of BitDevs in Brasília and in Porto Alegre, which is the city where I actually live. And more recently, I became a collaborator at the MIT DCI on this global research network that we are putting together. If you're interested in doing more academic research, or you know someone that would be interested on working on academic settings, let me know. Just reach me on Twitter or whatever, or I'll be here for the whole conference. Okay, so let's talk about the eCash. How does this thing work? Quick. It's based on a traditional banking system in which you have some kind of money, and you go into this bank and make a deposit, and the bank will print something, here, some kind of bill, and this bill is an IOU, and the bank promises you that if you give these bills or these notes back, you can redeem your real asset that you deposit in the first place. And the nice stuff here is that Alice can take these bills and use it just like money to buy, for example, some food with charge. I will call Alice Alice. I will be Alice here. I will be the user. The mint or the bank is usually called Bob in the specifications. I find it weird, but it's the way it is. So I'll try to use this naming here. Bob will be the mint. And just like in real bills, this bill is a better asset, so anyone, not only asset or Alice, can go back into the bank and redeem the backing asset. So this is pretty much what we are going to be doing on this eCash setup. Just like a real bill, the eCash is actually a signed serial number. This is what we are going to build. We are going to choose a serial number, and we are going to have the mint signing this thing, and this signature is what makes it worth to go back into the mint and say, okay, you signed this, it's a contract with you that you promise to redeem this money back. But contrary to banknotes, serial numbers that are actually issued by the bank here will not know which serial numbers are around in the bills that he already signed. We are going to see how this is done. So the cool part here is that the bank doesn't know who is owning which bill, contrary to a physical bill. So that they have this argument of privacy involved, and I'm trying to show you where this comes, this argument of privacy, and this is pretty much why I'm interested on this. But of course, you can see this is a custodial thing. In a Bitcoin set, you deposit Bitcoin, and you get these Cashu tokens, and you can transact with Cashu tokens, and then you can go back into the mint and take your Bitcoin back. This is the basic idea. Really quick into this ECC cryptography. What we need to know here, you can see my mouse. Oh yeah, you can see my mouse. Okay. What you have to know to understand this thing is, in elliptic curve cryptography, we have two basic data structures. The most basic one is, I will call it a scalar. It's just an integer number. And you can do pretty much what you expect with integers. You can sum them. You have this notion of a zero, which is neutral element. You have the additive inverses. And you can also multiply them. And you have this notion also of an identity for multiplication and a multiplicative inverse. And we also have points. And points are actually points in a curve, in a very specific curve. So they have an x and y coordinate. And they work like numbers for addition, so you can sum that up. There's a notion of an identity element, which we call a point at infinity. And you have inverses of points. But you don't have a multiplication notion among these points, right? You can sum them up, you can subtract, but you cannot multiply 2 points together. It just doesn't make sense. It's an operation that's not defined. But given that we can sum up points, we can define what we call a point operation, a point multiplication operation. I always find it confusing, but it's the multiplication of a scalar by a point, and it gives us another point. We usually call this in this setup this a small a private key. The result of the point multiplication will be a public key. In Bitcoin, it's just the same thing. And it's usual to call this B point that we started with a generator point. This is not the actual important to remember these names, but this operation here has the most important property that we use for cryptography, which is given small a and big B, the private key and a generator point, it's pretty easy to compute this new point C. It's an easy operation. But given B, and in this setup, everyone will know which point is this B. It's a parameter for the curve. But given B and given C, it's supposed to be impossible to calculate A without going and trying a lot of A's and just trying to brute force this thing. This is called the discrete log problem for the elliptic curve. And we are going to see this equation again. And this will give us a notion of a signature that we are trying to get with the match. Okay. Given that, how does this variant of eCash works? How do we acquire some eCash? So the idea is simple. Alice go into the mint, deposit some funds, and then we start this process of minting a new token. Alice chooses a secret message, which will be the serial number for the specific token that she's minting. She takes what I'm calling a blinding factor, which is just a random number. The important property here is that the mint cannot predict what this blinding factor is. So just take a random number. And then you do these operations. You take the message, you take this secret message, which can be whatever you want. It's also a good idea to have a random number here and just convert it to a string. We are going to see this hash 2 curve in more specific when we see the code, but it transforms a message into a point on the elliptic curve, which we are going to call y. We take this blinding factor and call it r, and Alice compute this b prime, also a public key, it's also a point, by multiplying the blinding factor by g. G is a pre-chosen point into the elliptic curve that we are calling the generator point for this curve, and sum up with y. And she will have this b prime thing, and she sends it to the mint. And she says, okay, I want to mint something. Here is what we are going to call a blinded message. It's a message. Here it is. It's a point in the elliptic curve. Okay. The mint will take this and he will compute. He will take his private key, which is a small a here, and the mint will multiply it by the blinded message, which is a point. It gives us another point. I'm not going into details because of the time about these DLEQ proofs, but those are two numbers that the mint will send us back together with C prime to prove that the mint is using the right key to sign this message. Because since Alice, we don't know small a, without this we have no way to validate that the mint is doing what it is supposed to do. So there is this cryptographic scheme to make this proof possible. So I'll get this. And if you look at the left side here, I'm keeping track of which information each party has seen during this process, right? So just by now, Alice has seen the secret message, the Y point, the blinding factor, and this B prime, and the mint has seen this B prime that it took from Alice, and it produced the C prime point, this ES proofs, and sent it back to Alice. So Alice has seen pretty much everything. So now Alice goes into a process of unblinding this signature. What she's going to do is she's taking this C prime that is the blinded signature that she got from the mint in the previous step, and she's subtracting R, which is the blinding factor that she chose, multiplied by big A, capital A, which is the public key of the mint associated with this private key that was supposed used to sign this blinded message. And it will give us this C, which is a point in a curve as well. And Alice will take this pair, the secret message, and note that the mint has never seen this secret message before. And we are combining this with this C, which is a point in the curve. And also, the mint has never seen this point before. It's just private information from Alice. And Alice will claim this to be a token worth of whatever she deposited in the first place in the mint. So this is a quite easy and clever way to produce a serial number that the bank doesn't know, and also we can make the bank to make a signature on this serial number, this secret message. And also the bank doesn't know whatever he's signing for. And also he never seen the signature, the final signature itself. So the bank does pretty much nothing at this point. And this will be the eCash token. So Cashu will also add some metadata together with this, but this is pretty much whatever the token will be composed by these two informations here. Given that, I have some steps here. Why does this work? Why does this work? Yeah, maybe it's nice to go over this. This is the operation Alice did to unblind the signature. And if I replace C prime by what the mint did, I have this equation here. And if I also replace B prime for what Alice produced in the beginning of the protocol, I will have this. If we rearrange this, and we are going to have this, and you can note that this factor here will cancel with this factor here, and we will end up with this. This is what Alice will have at the end of this whole operation, which is a point in the curve that was generated from the secret message that she chose and never revealed for the mint, multiplied by the private key of the mint. And this is a clever thing because the mint is not required to show the private key, of course, and this is how it's done. And this is very easy for the mint to verify. If I give it, I just say, okay, this is a secret message. What the mint can do is compute Y itself from the secret message and check if y times its private key matches with the C, with the signature that I also give in when I try to redeem these tokens. This is how I get my money back, and this is how the mint can be assured that, oh, okay, that came from a previous deposit, so I'm supposed to redeem. I'm supposed to have funds to fulfill this. Of course, we are trusting that the mint keeps those funds in place, so that you can go and actually redeem the thing. But there is another catch here, which is, okay, animations, which is, okay, what stops Alice from double spending? Because Alice can use this secret message together with the signature as a token. And I'll give, for example, take this token and make a copy and handle it to Pins to pay for whatever. And now Alice, have a copy of the token. Pins will have a copy of the token. So we have two copies of the token. I'm actually duplicating money right now. How do we prevent us both getting our money back, right, in the mint? The rule is, whoever presents a valid token for a mint first will get the money back, and then the mint will keep a database of secret messages that it already seen. So this should be pretty unique. So if you're trying to do this process here and you choose a secret message that was used before, then it will go through this process and you will have a token, but when you try to redeem it, the mint will say, oh, I have already seen a note with this serial number, so it's already redeemed, it's invalid for me. So you're screwed, by the way. So the best way to, probably the best way to choose these secret messages is by taking real big random numbers. So the probability of collision is, it's quite small. So this is not a problem. This is pretty much how eCash works in any setup. I'll talk more specifically now about the Cashu protocol, but there is also this Fatty Mint protocol, which is similar, at least on this part, but they have different transport layers and other rules for what is a mint and how a mint works. But this is pretty much how the same way at least for the tokens. Okay. The Cashu is a protocol that's specified by means of these NUT documents, which you all can find here in this address, Cashu btc.github.io/nuts. And there are actually two sets of nuts. There is a mandatory set that every mint is supposed to implement, and it has the basic functionality for this thing. Nut 0 covers cryptography that I just explained to you, and it covers models. Models are the data structures that will represent the tokens together with the metadata involved. Nut 1 specifies how the mint should build its public keys, how many keys. We are going to see just, a lot of keys in just a moment. Nut 2 specifies key sets. We are also talking about this, looking at the code, and how to charge for fees to undergo this process. Nut 3 is talking about swapping tokens. We are not covering today because of time, but it's how you can go into the mint and redeem new tokens. Because as you just saw, when I make a payment using these eCash tokens, the receiver of the token has now you have a race condition here happening. I have a copy of a valid token, you have a copy of a valid token, and whoever tries to redeem it first will get the money. So swapping is the process on which the receiver of the money goes into the mint and produces new tokens and invalidates the old tokens. So this is pretty much what has to happen. Minting is the process of minting. We are going into more detail. Melting is the process of giving tokens back and taking money back. And there is this nut6, which is some information about the nuts, the mint. There's a whole lot of other nuts and other specifications. For example, specifications for spending conditions, something like HLCs and all those kind of stuff. Really cool stuff happening on this Cashu ecosystem right now. And I encourage you to go and look at it. All right. The second piece of information that you need to know is Cashu is a web protocol. So the Mint is like a backend. It has some HTTP endpoints, and you just send some JSON around, and you just get some JSON around. So this is pretty much what happens. I'm not exactly a web dev guy, so I had some hard time to get around. So maybe I'm dumb, but it's okay. Here's a QR code again for my repo, just in case you need it again. Okay, if you want to follow along, there is a Mint online right now. It's a test Mint. It's on this IP, and if you are following with my code, maybe you want to export this, this environment variable called Cashu default Mint, and use this IP address with this port, and you have access to a Mint. And otherwise, you have to specify the Mint all the time on this starter code, just to make the code a little bit cleaner. I'll just give some time for folks who copied it. (185, 215, 164, 89), and the port is 3338. Okay. Okay. So let's see what we have on this repo. I hope you can see what I see. If you go there right now, there's a wallet folder with some source code and pretty much 6 or 7 files. I'll go through them, and then we are live coding something, just to make it fast. Oops, I'm doing something wrong here. Yeah. Okay, the CLI.py, I'm using Python here. I'm not a Python guy, but I just thought it would be easier to explain things. This is the main function of this wallet. This is what will be called when you call the wallet. The wallet is called Cashu/WS for workshop. This is what will be called. We have a main function here. It's just parse command line arguments, and you have a whole bunch of commands that you can issue. Maybe it's easier to show them here. This is pretty much what you will have available. And the idea of the workshop is that you go and implement all these commands here, which covers pretty much all the basic functionality of a Cashu wallet. It can be done in maybe a day or 2 working days. It's not that hard. But just because I have 50 minutes more, I will try to go into try to make it a little bit faster. Sorry. Second thing that you will encounter here is the crypto.py file, which is the crypto library, which pretty much imports this SecP256 library. It extends it so that we can use Python operators for summing points together and multiplying them. This is pretty much what's here. And we have this hash to curve function that I mentioned before. And the way it works is this. We have this message, which is the secret message that Alice chose in the beginning. We concatenate it with a domain separator that's specified in one of the nuts. We hash it with SHA-256. And then we will try to, we'll combine it with a counter, which starts with 0. And then we will hash it again. This hash will be interpreted as a number. And we just say, okay, is this number a valid x coordinate for the elliptic curve? If it is, it's the point that the result of the function. If it is not, we just increment this counter and we try again, right? It will eventually get you a point in the curve. The probability of that happening is like a half each time you try. So you will probably get a valid point out of this, but there is a timeout of 2 to the 16 tries, and this is pretty much how it works. So it maps messages into points in the curve, and it's a deterministic mapping. The second thing that you have here is this token file, in which we have this class called proof, which will be the final token that we are going to build with the Cashu metadata. You can see there is a secret field, which is the secret message that we chose. C will be the unblinded signature that we produced together with the mint. The ID is an identifier of which set of keys from the mint we are referring to, because the mint can keep a whole lot of different sets of public keys and private keys. And I was thinking about, okay, how can we use this? Why have different sets of keys? Because that involves some rotation of keys and it's a complication. But just before this workshop, I was talking to a guy, I forgot his name, but he's working on this eHash project, which is, you get, it's for miners, for mining pools, and whenever you give a valid share for the mining pool, it gives you back, it's not a Cashu, it's an eCash token. And that represents an IOU that can be redeemed after the pool itself finds a valid block and gets the block reward. And then the pool will have funds to redeem this eCash tokens. And then the guy mentioned, okay, but we have this very specific problem, which is, okay, what do I do after I found this block and then I want to reset the epoch of the pool? I want to go into a new set of shares to consider for the next block. And if I understood it well, they do this by rotating the keys on their mint. So this is a clever way of identifying which block belongs that share IOU that you received. I don't know how useful it is, but it's an interesting application at least. And you have this amount that corresponds to how much you can redeem using this eCash token. I'm not going into the details here, but you pretty much have methods to serialize and deserialize this thing to a JSON file, to a JSON data structure. So this is pretty much it. Next thing is this wallet data structure. And this is, I'm sure that all of you can do a better job than I did here, but this is the data structure to persist some information on my side. Because you saw Alice will have some private information, which are the tokens, and if she loses her tokens, there is no way to get them back. So she's effectively losing money. So we have to have a way to persist that data for later, for using this later. And this is what I'm doing with this wallet data structure. I have some information here about the mint, the units, it's in sets most of the time. It's nothing more than a JSON file in somewhere in my machine. And so I keep a path, some metadata, and I have this list of proofs. And the proofs are how the tokens are called in the specifications. So this is pretty much it. I have methods to, it's like a stack of proofs, so I can push things into the wallet, I can pot things from this wallet, and this is pretty much it. Next, we have, this client data structure. As I said, Cashu is a web protocol. So what I did here is a translation layer from HTTP endpoints and Python functions. So just to make it a little bit easier to deal with these endpoints and send stuff and get stuff back, communicating with the mint using code here. So I pre-made a method for each endpoint that's important for the basic stuff. Each one is specified in a specific node. So for example, there is this keys endpoint that's specified in node 1. There's this info, which is node 6, and we are going to see what they do in just a moment. And finally, we have this commands file, which is where the main logic of the commands live, of the wallet commands live. So what I'm going to do is to code some stuff with you right now. Let me start with the easiest command, which is info, which has an endpoint called info in the mint, and it gives me back some information about the mint. Okay, so let's implement it. I will, of course, cheat to make better use of time, and I want to copy this, and I want to select that, and boom. Boom. What I did here, real quick. I just called this init wallet function, which is a helper that, tries to find the wallet file. If it doesn't exist, it creates a new one. If it does exist, it loads a data structure in memory. It initializes the web client, so I can make calls for the mint. Maybe this is not the best function name, I just realized. Maybe it's init something, wallet and client, whatever. And then I use this, the client info method, just to, and it will go into the endpoint. This method doesn't require me to send in any information. It's a get method, get HTTP request. And I'm also printing whatever is in my wallet right now. So if I save this and if I run that on my mint right now, this is what I get. I get a JSON back. As I said, a lot of JSONs going back and forth. It has a name of the mint, a pub key, a version of the software that it's running. There are a lot of implementations of mints out there. Descriptions, contact information, message of the day, whatever. Important thing here is which nuts this mint supports. It's supposed to support all the mandatory nuts, 0 through 6, but it can also support additional functionality, additional features. In this case, it supports nut 7, 8, 9, and so on and so on. And here is, I already have some tokens. I was not expecting this. Okay. This is what's on my wallet right now. I have some information here, metadata. I added, I need to know the mint, which mint it's supposed to I'm supposed to go and redeem these tokens. And if I'm paying someone else, I'm supposed to tell, okay, this is the mint you're supposed to go and redeem this thing. And we have some proofs here, and proofs are the actual tokens. And as you can see, I have some. I have 3 tokens, each one worth 8 sats right now. And they have this amount, an ID that, as we'll say, identify public keys in the mint set. A secret is the serial number that I chose, and the blind signature that I built together with the mint. Next, let's do this keys. This keys method. Also, really simple. I just initialize everything, and I call this keys endpoint. I am not required to send any information. I can just get some information back. And what the mint gives me back is this, and it's called a key set structure. As you can see, it's a list of a more complicated structure, which has an identifier for this set of public keys. In this case, the units they are supposed to represent, for in this example, sets, and a list of keys. And you can see this is actually a dictionary. There is a key for a public key called 1, a public key called 2, 4, and a lot of powers of 2, and a lot of powers of 2. And why is that? Why is that? In principle, I can go into the mint and make a token of whatever denomination I want. So I can just go into the mint and say, okay, give me a 513 sats token, please. And I can just mint that. There are 2 problems with that. 2 problems of doing that. First one is, if I want to use this to pay whatever payment, which is not exactly 513 sats, I can't just use that. I have to go back into the mint, return this 500-ish token, and mint new tokens with at least one that makes for the payment that I'm interested in doing. So this adds some friction into the thing. The other thing here is, if I'm allowed to mint whatever denomination I want, it's reasonable to suppose each one in this room would mint a different amount, a token with a different amount. And that would allow the mint to identify us. Not because it has seen my secret or serial number, but because, okay, there is some guy using this IP trying to do a token with that specific denomination. And later on, I pass this for someone else, and that someone else will go into the mint and try to redeem or refresh this token, and it will give the mint that token, and the mint can say, oh, nice, I know that I can now track the payment path that underwent on the offline payment between the peers. We don't want this to be possible, so what we do? We mint tokens in powers of 2, so we can represent pretty much any number, and we split whatever denomination we want into this a set of different tokens, but they are all standard tokens, at least in the amounts. So this is why you have all those keys here. In this example here, I will just use, I will mint an 8 sats token. But it's not much, the process we are going to go here is not much different to go and say, okay, I want 3 tokens of 8 sats, one of 16, one of or 10 with one set. You can just do this in a single operation. So these are keys, mint keys. What do I need now? Okay, let's go into the process of actually minting something. It's not exactly involved, but there are some steps that we have to go under. First, I have to pay the mint. I have to deposit some funds in the mint. It's the first thing that I have to do. Oops, I'm not supposed to do it. So, okay, how does that start? I go into the mint and I say, okay, please give me a Lightning invoice, and I'm supposed to pay this Lightning invoice, and you are going to receive some funds. This is how I deposit things on these mints, at least on the Bitcoin implementation of the thing. So we need some way to go into the mint and ask for a quote, which is a Lightning invoice together with some other information. And of course, I'm going to cheat again. And I have a helper function to do this for me. This is it. I have this mint quote bolt 11. I'm not a Lightning guy, but I think bolt 11 specifies the invoices themselves, right? I tell them how much I want to deposit and the units of which money I'm giving them. And this is what I send to the mint. And then let's do it. And we are going mint quote amount 8. This is what the mint gives me back. There is a JSON which has a quote identifier. I have to keep track of this to refer to a previous payment. I have a Lightning invoice here that I'm supposed to pay, the amount, blah, 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 and the state, which is unpaid right now. I'm supposed to go unpaid and pay this, and the mint will identify this payment, and it will mark it as paid, of course. And then I can continue through the process, with the process of actually minting the thing with the blinding signatures and all this stuff. Since this is a test mint, it will automatically mark it as paid by right now, and we can check it. We have another endpoint in Cashu, which will be this one. Which will be this one, mint quote get, which is how it's called, I believe. And what I can do is say, okay, give me the status for this quote. Oops, what I did wrong. Sorry? Yeah, huge. Mint quote status, of course. And you see, I get pretty much the same information, but it said me, it just updates me of this state if this is already paid. In this case, it's already paid. We already deposit some funds into the mint. Now is the fun part, which is this function mint execute. Where is it? Mint execute, this one. Let's go this a little bit slower. So let's remove this. So, okay. So to start with, oops. What am I doing wrong with this? Let's initialize the thing again, get a client, get a wallet, done. We are supposed to get a quote, which I showed you how it's done in the command line here. Then I'm getting the quote back. it's always a good idea to check if the quote is paid before proceeding. Otherwise, I cannot, it doesn't worth going into the process. So I have deposited some funds in the Mint. The next step is, okay, let's generate a secret message that's going to be the serial number for the thing. So I just take a 32-byte random number. I pass it through this hash-to-curve function. This will give me the y point. And I just take an R, a new private key. In this case, when I ask for a new private key, it will just provide a random number for me. Then I have to take the Mint keys. Now I go into the Mint again, ask for the key set, and here I'm just processing, splitting separating this keys dictionary, because I need the Mint public key to actually continue with this process. Then next thing is I create a blinded secret. I just hide my secret with this R factor that we saw before. I have this I'm building here this output stuff, which is the actual information that the Mint expects me to send it to start the process, which has this B prime that we saw on the crypto part, but it also has the amount that I want to mint. I have to say, okay, I want to use this specific public key here. And I say, okay, I want to use this specific set of keys because the Mint can may have a lot of sets of keys at the same time. So I just say, okay, I want to use that specific set. Then next. Then next, I send it to the Mint to get the blinded signatures. You see that I have to put it on a list. So if I want to mint a lot of tokens at the same time, I just go into this process of making a lot of these outputs. So I just repeat this process a lot of times, just a loop here. And you build this list, and you send the whole list of whatever you want to mint to the Mint. The Mint will respond me with the blinded signatures. And next, what I'm going to do is, okay, let's take the blinded signatures. There will be a signatures field. I take the first thing it's returning me a list. I give it a list. It returns me a list with a blinded signature for each element of the list that I sent. So I just sent a list with one element. So just take this one element back. And I turn this into a public key so that I can make some magic with it. Now I have the blinded signature. I have to unblind it, which is done by taking the Mint public key, which is a capital A. I'm supposed to verify this DLEQ thing. I'll just skip that. Then I have this. Yeah, sure. But you have to speak a little bit louder.
Yeah, on that line, string quote amount, and then you're pulling from the keys if you don't have one that matches exactly, right?
Sorry, I didn't.
Meaning, like, so if the quote amount is
quote amount.
3, you're not going to have that in the dictionary, right?
Yes, and then it will fail here. If I understand well, if I'm trying to access something that doesn't exist in this dictionary, which is in the right screen right now, is that the question?
Yeah, it'll fail.
It will fail, yeah. So you're supposed to check if your software is supposed to check this.
Okay,
if you're
make sure
failing
that
or not. Sorry?
Okay. So making sure that the quote amount is an amount that's part of the key,
Yes.
key set.
Yes.
Okay.
And this quote amount is the amount that what I'm doing here is I'm asking the Mint, okay, sign this thing for me using that specific key. But that's tied to a specific amount. So if I give the amount, some amount that the key doesn't know how to sign, it will fail sooner because I will just send this to the Mint and this will return a JSON with an error. And I can say, oh, okay, the Mint doesn't know how to sign tokens for this denomination. But this is why you are supposed to get the key set first and see what the Mint can do. So you can always verify and say, okay, I'm sure that the Mint can sign this amount for me. Sure. So we got the C prime. We can unblind the thing by doing this, which is the unblinding part of the thing, and it ends up with this C, which is the point in the curve that represents the Mint signature for the thing. I have some verification steps there that I will just skip, and I'll just go straight to this part here, which is building the final token data structure. So I'm taking the secret that I generated, the unblinded signature, the key set of the Mint, and the amount, putting this together into a JSON, saving this into my wallet, and then persisting it into my wallet. So by the end of this, I'm also printing so that we can see that happening. So if I didn't do anything wrong, I can just do Cashu Mint. I have to refer which quote I'm trying to consume. These are the deposit that I did. It will go into the internet and do all this process, and I have a new token here. This is pretty much it. And if I see my wallet again, I have this info. I have this new token here, and the way I use it to make a payment for someone, I just send this JSON to someone. If you go into the nuts, I will not have time to go into this, but if you go into the nuts, there is one of the specs that tell you how to encode this JSON info into an actual address or this Cashu strings that you see around, or make QR codes. There's an encoding for that, so that you can transfer these tokens to anyone else. So you just take this, you send to someone else. And what I do with those, I can do pretty much two things. I can go into the Mint and refresh them, which in the Cashu parlance they call it swap. So you just go into the Mint, send this token, and you get a new one back. And the process is pretty much the same that I just did for the minting. I have to generate the secret, a blinded signature, send it together, and pretty much the same thing. Or I can go into the Mint and redeem my money back, which is called melting. So melting, it goes like so. The first thing that we have to do is, I should go into the Mint and say, hey, I want to get paid back in Bitcoin, in Bitcoin specifically. So I will send you a Lightning invoice, and afterwards I will send you some tokens, and please please pay this Lightning invoice so I get my money back. This is pretty much what is going to happen right now. So I have something here. Even though this is a test Mint, it requires a valid invoice. And so what I'm doing here, I'm just going into Wallet of Satoshi, taking a Lightning invoice, and that's it. And this is a real address that you can deposit some tips if you appreciate the workshop. Of course, by this time, this is the first time I'm doing this workshop. Maybe feedback is way more appreciated than tips, but come on, tips are always nice. So I'm just taking a Lightning invoice with that function there. I'm supposed to go to the Mint and say, okay, here's my invoice. I want to take back that much Bitcoin on the Lightning invoice. My test Mint is configured to not take fees, but the Mint it can charge fees, so you have to consider these fees for getting your money back. Fees are a thing, right? So right now I can do get melt invoice for an amount of 8. I believe it. Oops, what I did wrong. Does anybody see what I did wrong? I know what's wrong because I renamed this thing in the last minute. Yeah. So I have this Lightning invoice. I'll just save it for later, and I have this melt quote, so I can go to Cashu, blah, melt quote. Put an invoice here, and it's supposed to return me something similar to the previous one, which has a quote, and it says it's unpaid right now, and it will stay like that because it's only supposed, now it's the Mint that's paying me back. So it's supposed to only pay me back once I present the valid tokens for this amount of 8 sats. So I have some tokens that I can spend, so just do this real quick, which here is called Mint Execute. So I initialize everything. I have a list of proofs in my wallet. So I'm just saying, please give me the first proof that you find. Right now, I'm just minting 8 sats proofs, but a real wallet should take this and do some kind of coin selection, try to select the tokens required for that specific amount. I still don't have that implemented. So what I'm going to try is, okay, take those proofs, take the list of proofs, send it to the Mint endpoint that's called melt/bolt11/ I have to provide the quote ID that I have on the right side here. If everything goes okay, the Mint will pay me on Lightning. It will validate those tokens. It will add those serial numbers into the database of invalid tokens, so they cannot be redeemed anymore. It will give me back a message just saying, okay, it went well, we are going to see. And then I do some cleaning in my wallet, just remove this proof and then persist the new state of the wallet. It's important that it's kind of a catch, because when I was studying the source code of some projects to see how they work, I don't remember which one specifically. It was a Rust implementation which removed proofs from the wallet state before validating that the Lightning payment was already received. But this is quite dangerous because that Lightning payment might fail, and you might already messed up with your tokens. And by this time, if you lose your tokens, it's a better asset you have. If you have no copy of this, you are going to lose your funds. So it's always best to send them to the mint, and after you're pretty sure that you got your money back, just remove those proofs from your storage. So take care of this. And if this doesn't work, what I'm going to do is I'll just print some stuff and say, okay, this went sour, and try again, maybe. So let's see that happening. So I can do melt ID. I'm supposed to say, please pay this back. You can say it takes some time because it's supposed to be doing a Lightning payment. So here's the quote, and this is the confirmation from the mint that it paid the quote. Of course, I can real wallet implementation would go into the Lightning wallet and check, okay, this specific invoice was paid, but you can also double check this. You don't have to trust the mint itself. Of course, this is a test mint, it's not paying anything, but you can see what's happening here. I think I will wrap up. This is pretty much the whole process. What I did not show you, I did not show you the process of going into the mint and refreshing those tokens. But the process is pretty much the same as doing a new token. You have to go and make a secret, blind it, send to the mint. There is a different endpoint for swapping, and you can go into the specifications. You get back those blind signatures, and you're supposed to unblind those signatures and make up new tokens and use those new tokens. So this is pretty much it. I think this is pretty much it. I'm finishing ahead of time, so maybe we have some time for questions if you want. Anybody? Sure.
I wanted to go back and review the key
Here?
sets.
Sorry? Oh, the key sets. You want to see the key sets again?
Yeah, I'm not. Are these key sets? So they always want. I mean, they're powers of 2, but is it always 1, 2, 4, 8, 16, or is it?
Yeah, they always go. It's also a specification that they should go into powers of 2, because then you can represent any denomination that you want.
So would you...
At least integer numbers, right?
Say it again. What'd you say? I didn't hear you.
At least integer numbers, you can represent pretty much anyone.
Oh. Meaning if you combine... So
yeah, for example, if I
wanted 10, you'd do 8 and plus 2.
Or you can mint 2 tokens of 4 and 2 tokens of 1, for example.
Okay, that makes sense.
That makes sense? It's like going into the bank and say, oh, I want to take $100. But the bank can give me a $100 note, or 10 bucks notes, or 101, or a mix of those denominations, right? This is pretty much the same thing. Yeah, right. It's actually a good thing to have different tokens in your wallet, denominations, so that you are more equipped to do different payments without going into the mint again and trying to replace those tokens because you don't have a node. As you can see, this is an interesting thing that I just came along. It would be cool if we could exchange tokens, right? Because, and this is a problem that I had a student last semester that did a project which was a swapping protocol for eCash tokens, this specific tokens. And what's the problem? I started with this exact problem is, I want to pay you $40 or 40 sats, or maybe, I don't know, I want to pay you 30 sats, but I only have a token of 32 sats. Right now, what I'm supposed to do? I'm supposed to go into my mint again, give it back the 32 sats, and make up other tokens so that I can combine them and pay 30 for you with a lot of different tokens. But what we did is, suppose that you already have some tokens yourself. You also have some cash. Why could you not give me some change? Without we requiring us to going into our mints. And we developed an atomic swap protocol on top of this to do exactly that. It's kind of silly just to say, oh, I want to make some change, because all the wallets just go into the mint, refresh tokens, and make the payment. But there is one interesting case that's not covered, and it's not, maybe there are some people that are thinking about it, is the unit here, the actual funds that are backing these tokens. All the mints that I know work with Bitcoin. Of course, this is a Bitcoin world technology. But they are not required to. There is nothing stopping you of having a mint in which you go and deposit dollars or euros or reais or whatever, or miles from the American Airlines company, or whatever you want, and issue these eCash tokens. And one interesting use case would be, okay, now I have a mint of dollars and a mint of Bitcoin, and I want to exchange dollars for Bitcoins. So instead of going to the mints and doing Lightning protocol swaps that the mints already do, we cannot do that in this setup because dollars don't have a Lightning network to call them theirs, right? So what we do, we use this atomic swap protocol so that we exchange those tokens atomically, and then we just live our lives without. We require some support from the mints, but it's the features are already specified. So we need something similar to an HTLC to perform this. But the mints already implement that. It's not special for this kind of protocol. But it's something that I have some people working on. I hope to have this kind of banks in the future. Anyone else? Okay, guys, thank you. If you have some feedback, just open an issue on the repo. Harsh feedback, whatever feedback you want, it's pretty much appreciated so that I can improve this for other editions of the workshop. Thank you for having me.